Now, this is a process that we can do for any function as long as we can take unlimited derivatives of the function. So if you give me some function f, I don't actually care what that function is, so long as it has infinitely many derivatives that all exist. Then I can look at the Taylor polynomials, right? I can just take n different derivatives of my function, use those derivatives to find the coefficients for a polynomial. And those were the Taylor polynomials that I called T sub n. So the degree of this polynomial is its degree n. Each of these is going to have a remainder, which is just the function f minus the Taylor polynomial. So the question of whether or not f of x, my function, is equal to a power series comes down to whether or not this remainder right here eventually goes to 0. In order to work with that, I'm going to need a formula for what that remainder actually is. And I'd like it to be a formula where I don't actually care about whether or not the function has a power series, right? I'm trying to figure out if the function has a power series or not, so I'm not allowed to assume that it does until I'm finished with my calculation. I need to establish that functions do or do not have power series representation. So the key idea is that I can always write a function as equal to its nth degree Taylor polynomial plus some remainder. And the question is whether or not those remainders actually go to 0 as n goes to infinity. So we're going to need a formula to calculate that remainder, or at least get an upper bound for it. And that formula is right here. So if the n plus first derivative of that function f is less than or equal to some number that I'll call capital M in absolute value. Right, so notice the absolute value bars here. And if this is true, so long as x minus a is less than or equal to d, so you can think of d being the distance x is from the coordinate a. If both of those, if that is true, then this inequality is also true. That my remainder must be less than or equal to m divided by n plus 1 factorial, which is then multiplied by the absolute value of x minus a raised to the power n plus 1. So this is going to give me a formula for calculating whether or not the remainders go to 0. And whether or not the remainders go to 0 determines whether or not the function can or cannot be equal to a power series. Again, some functions can, some functions can't. And this is the test we're going to use.